I expected in service level checks. Wind, second story shear.
Why'd you ignore self-weight?
Why did I ignore self-weight? Because it was easier to do. And I could do
Wasn't a valid
it.
reason to do things.
Because I wanted to. I mean, from a validation standpoint, like, do I want to validate that VA can handle the members, like every self-weight? Yeah, there would add some value there. The chances that they fucked that up are probably pretty slim. The chances are that I messed up putting into the VA model the right loads to get the overall dead load. That's what I was more worried
You might have had a
about.
wrong member in there.
Totally, yeah, and that there's an extra validation there, and that's where I get a grin and say, I didn't have to do it, okay? But some of you did. Which is fine, okay? Which is fine. And it'd probably be good. Did anybody, no, I don't think anyone found an issue that way though, did they? Or at least not in the cows.
I got docked 2 points for some reason though, even though they managed.
Oh, we'll have to talk about that later then, James. We'll have to talk about that later.
Project money.
Yeah, that's it, yep. Yeah. So second story shear due to wind, right? So this is, and I gave the definition of it because I think it's somewhat misleading in the description there, right? Or in the language, but it's really looking at all of the level loads above the level of interest. So if I ask you for the second story shear due to wind, that's essentially all of the loads that you were putting on all of the subsequent floors above it, okay? That doesn't mean you reduce the loads to the floors above it. You consider all the loads that you had to the floors above it. Some of you reduced that based on the fact you thought you were coming in at halfway above the story. It's all the loads that you imply on your model at every level above the level of interest. So the second floor, you're looking at the third, fourth roof, sort of thing, okay? So in order to do that, and you guys had a wide-ranging thing of ways of doing that, I essentially took my model, I pinned it at the second floor, and I looked at that in the one direction. In the other direction, you couldn't do that because in the moment frame direction, your columns were fixed, right, across that story level. So if you fixed it in translation, the fact that this upper floors were getting pushed over, we're actually trying to pull back on the lower floors, right? Because you had this continuous member that was bending over the course of 2 floors. And so it would become inaccurate, right? And the reason why I found that out is because I did pin it that way, and I'm like, what the fuck, this should be just the same. And then I started thinking about it, I'm like, well, you have this continuous column that was running through. So then when I did it the second time, I actually looked at the shear within the column. So in the longitudinal direction, I just pinned at the second floor, got all my reactions. In the transverse direction, right, when wind's hitting the big broadside of the stair tower, I looked at all of the shear in the columns in that story, and I could add all those up, and all of that worked out, okay? Yes, Elias.
I'm looking at your story shear calculation. I'm kind of confused where that trig area is coming from.
The story.
Your hand calc for the story shear. 60 minus 7.5 minus 15.
Yeah, so
Isn't it just the 2 stories above? Shouldn't it just be 15 times 30 feet?
yeah, so we had 15, 15, 15, and 15, right? And I wanted to know what the story shear was at the second floor.
That's the second floor?
Yeah, so it's everything.
I think everybody
What do you mean?
read that differently.
That's the first floor.
It's
Or like,
between the two.
This is first floor.
that's first floor. Well, the first story is that first story is
I'm
there.
glad you didn't pick that up in my.
It's second story shear.
No, you guys did it. Yeah, it's second story shear. When you look at the definition, it is all of the.
Shear above that story.
They're more specific in saying it's the. I don't have
Surface
it.
of the floor.
Yes, so it's essentially before. So regardless of looking at it this way, right? If we looked at it the entire building, we had loads coming in at all these diagrams, right?
It's really PSF load.
They were,
Across
either along the length if it was wind or down along each one of these beams if it was seismic, right? So each one of these was coming in at a level. When you look at story shear, what they ask is what's going on above the diaphragm at that story, like everything above that level that is acting at these levels. So your tributary area at that point, for me, was everything above here. So this distance is 15 feet, and this distance is 7.5 feet. And I took 7.5 feet off because, and so, I mean, some of you did it where you, even in some of your models, you put this load into the nodes at the base of the structure. And I
You said
think,
global in it, it was
Yeah.
like, that, normally you don't do that, but.
I understand, I
global.
didn't dock points for that, okay?
Yeah.
If I did, come talk to me, okay? Cause it took me forever to grade all these. Imagine opening up all the VA models and being like, did you do this right? And like looking through and checking the reactions. So, if you looked at the construction of this stair tower,
Wait, but first of all, I think what most people are confused about, or this is what I'm confused about, is I think I did the second floor as the next floor up from where you're looking at right now.
Yeah.
no, so
Like,
I
that's
really.
the first floor.
Okay, look at it like this, in your problem statement,
Yeah,
when you
no,
gave
that's-
the earthquake shears, when you gave the story shears for the earthquake loads,
Yep.
you go first, second, third, and.
Roof, exactly.
Oh.
Exactly.
I mean,
So,
it's just like, you know, you do the
I
same
was so
process, it's not that big a deal.
Yeah. I didn't see that.
I would agree
That
that
was-
does look
that
like
was
the
wrong.
second floor.
So it,
That was second, third, fourth.
That's the second
Cause
story
I kept
floor.
going back and
I
forth.
think it's because I
And then I
added.
saw this and I was like, okay, I'll go with that.
Oh shit. Yeah, sorry.
Alright,
Yeah,
you
this
know,
is the second floor. Thank you, Amanda. Okay? If you have any gripes about that, you come and talk to me, okay? If I didn't benefit you, okay, then we can talk about it.
What is the like typical way of labeling
Yeah.
floors, like in industry? Do you go like ground level, first level, or?
Yeah, I mean, usually ground level is the first floor.
So
Yeah.
ground and first floor.
Is it like ground is the first floor
Yep.
and then the second? Yeah.
Yep.
That's second.
What if you said first level, is that? like
That would be this.
The walls.
But see, one thing that was different is, like, some of you took the tributary width from, because when I originally loaded my model, I had trib width to each one of these diaphragms is 15 feet, right, halfway between story height. But I let go of this, right? The reason why I let go of this is because generally in construction, and looking at this stair tower, right, there's cold form steel studs in the wall that frame from the ground floor to the second floor, right? First floor to second floor. First elevated diaphragm, all right? Okay? And so those studs are spanning vertically. And so that load, when you get pushed on with wind or even with seismic, yeah, that load is going to span up and downward at, half trib up and down. Okay? And so that first one's gonna come straight down to here. What I didn't tell you is that down here at this ground level, usually there's a concrete wall with a continuous footing underneath it, and that wall is going to carry the out of plane load, and it's not going to travel back to each one of these individual column piers. And so you kind of let go of that when you're designing the.
What wall? What wall or what?
So there's a foundation wall
Oh,
that's
so
running
the
between
foundation.
piers, yeah, so if you like
That's
look,
connected to those columns, right?
it sure is, but if you look at
So
it
you
like
have to
you,
load the columns to get it there, right?
no,
Lower
because
down the
this,
strip footing.
this is going to be, there's gonna be these studs that sit here on this wall, right, and they're framing upward, this is like looking at a plan view, right, we've got our
Oh,
mold
yeah.
frame columns.
Oh, okay.
You come
And
to
so
that
these
low.
guys are pushing on the foundation wall with this 7.5 foot of trib, whether it's wind load or seismic load,
Gotcha.
right? And this wall is then pushing on soil, right? And so it's gonna resist that out of plane loading, and it's not gonna have to get over here into these columns.
Okay, I see.
Okay. And that doesn't mean to say that that's always that way, right? You could have a different, like if you had really shitty soils and maybe you decided to like have like a grade beam here,
So it looks
and
like
that
it's
grade
bearing
beam
on it, yeah.
like pushes and then spans between these two piers, that could happen, right? So just thinking about the load path, which is good. Okay, so that's the story shear.
But it's of the 2 stories above that floor, right?
I thought you wanted us.
Yeah,
I
so
didn't-
so like if you
So
cut
why
it
would
here,
you
then
include
the
the
tributary
tributary
width is a set, or the loads that you would look at are all of the loads on the levels above that level of interest.
On the stories above that level
Yes,
of interest.
yes, and so you don't need to change
That's
the
the first-
tributary area of what's hitting this diaphragm, because it's going to be there. You're just looking at what is going on, everything above this level. Like you don't have to manipulate the forces at all the level. You're just essentially saying, I'm gonna cut my structure and I'm looking at what's going on just above that second floor. Okay? Some of you took and they, instead of having this as tributary width, like got rid of this and said that it was just what was hitting this.
So that portion of that load is still tributary to that diaphragm, so it's considered part of that story shear. Is that?
This?
The part which is Xed out.
Yes, so it runs up to here and you should have included it. It should have been part of
But
it.
that's not the story. Like the story's not that level. It's the in between those loads. So it's like the load that goes in between those.
I
two.
wish I had the definition.
That didn't
You-
help very
I mean,
much.
It was from floor surface to floor surface.
It was, yeah, I
Which
thought
is
it was,
opposite.
I thought it was
That's why I was
very
like, this-
clear.
That was why I
Yeah.
had that
That's
comment, which
confusing.
it sounds like you got a little offended. He said not useless to me. 'Cause I said
Well,
it's
because you
useless
were
to-
saying, no,
I was
no,
saying, if it, so the way the code reads is like you should take everything from this surface, load, like all the load above this surface, and I'm like, we didn't even load it that way, that's not how the loads span.
No, it said,
So why
what
wouldn't I-
was coming in, there's an aspect of that definition that includes levels. And
See, this
we'll
makes
talk
sense.
about it
This
on
is what I was
Monday.
arguing, is that this is better, but I thought that it was saying like, take that extra 7.5 feet that you're saying don't
Down-
include.
down here?
Yeah, and I was like, I
Yeah,
don't wanna
no.
do that, we didn't
Because
load
it
that
goes
way.
to
Like,
this
I'm not gonna learn
diaphragm at the
anything.
second floor, and so you don't need to worry about that, because the way the definition reads, it talks about like levels, right, or diaphragms, so it's, whatever load was there, like, keep it in there, how's it
So
read?
it's the
Elise?
summation of design lateral forces at levels above the story under consideration. So we're looking at the story, and the story is from here to here.
Yep.
So above that story would be above, like,
Yep,
would
but
be
when,
those two above.
but in that definition, it says design levels, right?
Yeah.
And so it's saying,
Levels above.
and so you were putting that there when you're designing, right? Whether or not that load came from this trib or not, whatever you put at that level in your model, you need to include that, because that is the design level load at all of the levels above. So
So
you
it
don't
takes
need to
into-
manipulate this tributary area and the
That
force
takes
at
into
that
account
level.
below that level. Like, those are lateral forces that are acting below that level.
So the
It's
code's saying no matter
tributary
how
below
you
that.
load it, just however you load it, everything above, account for those
Yep.
loads, like don't reload it.
But
That's what I was saying.
And
is I
maybe
don't
it
wanna
should have been,
reload this thing.
It was
I'm
confusing.
gonna make
I
a note,
didn't
because I'm
reload
gonna
it, and
change,
then I
I'm gonna
decided
change
to
it to
because of
seismic
the
load the next
definition.
go around, I'm gonna make a
Yeah.
lot of changes, obviously, but I'm gonna change it to seismic load the next go around, because that's very cut and dry when it comes to like level loads. And if you notice in the
Because this is a
definition I gave you,
PSF.
I got rid of the word that
Was
said
it
seismic,
seismic?
okay? Alright,
Honestly,
I'm
don't
learning.
include the
We can
story
talk more
here.
about Elias though, okay? We can dive into that more later. So then we checked the final, that northeast column, right, which was part of the brace frame, and it was very, very close, right? Very, very close. I think most of you got it. That was very, very close. If your axial load was a little off, the reason why it was a little off is because you didn't have dead loads, right? You got rid of the dead loads to check the service case, okay, but then you never put it back on when you checked the overall demands. Yes.
I assumed for the longitudinal direction that I could just take the components of the brace forces
Yeah,
at that level.
yeah.
Would I lose out on anything? Like, is there any like inherent stiffness that happens at any other nodes?
It depends on your fixity of the columns, right?
Yeah.
Because like I left the columns continuous, like from the ground floor, the first floor, all the way up to the roof.
Yeah.
And so there is some inherent stiffness for those columns to like resist bending, right, between floor levels. And so there would be a little bit of shear in those columns that you might not grab. The braces are significantly stiffer,
Yeah, I drove
right?
both.
Some of you decided to, for some reason, fix the brace frames in the out of plane direction at the ground level too, right? Which would also add stiffness that wouldn't really be there, and you'd have to design for that if you went and like model this and use those results. Because even though the brace frames are super stiff, right? The second you start pushing on it, there is displacement compatibility in this whole thing, and so when you move that, say, 1 unit of displacement, there's going to be forces at the bottoms of the columns in the weak axis, right? So what I was really hoping for is you would fix translation, but then rotation would only be fixed in the plane of the moment frames, right? They didn't have to be fixed torsionally either. Some of you decided to do that. But if you had your releases in such a way at all of the other floor levels, if you didn't release it torsionally at the base, like fixed it torsionally, then when you put a wind load that was a weak axis bending on one of the beams, and that beam wasn't simply supported at the ends in the weak axis, then that beam rotating is going to try and rotate the column, and the column is going to have some rotational stiffness at the bottom, right? And then you would get a torque at the bottom of these columns. And if there's a torque there, you're going to have to design for that, right? So anyway, most of you got this. One big thing was that some of you forgot was, if you were to have these two models, what would you compare, right? And where would you compare it? And there was all sorts of ideas, okay? And there wasn't a right or wrong answer here. I was just curious your thought process of what would you look at and why would you look at it? Okay, some people said I'd start at loads, some people said I would start at deflections. I'd look at all of the service case deflections at the top columns of this building and see, how they compared, okay? Connection used to resist torsion of the column at the moment frame, we talked about that on Wednesday, okay? All right, that's the homework. Let's do this one really quick. All right, I'm fucking jacked about this, all right? So this is the scoreboard, all right? At the
Saw this
stadium.
last night, and I was like, God damn it.
I'm jacked, dude. This is sick. Okay. So, and we're gonna talk a little bit about this. What's that?
Oh, he asked me if I did any work on this, and I said, I hope not, it'd fall over.
This is a Morris Merrily project. I don't know about the dirt side of it. Maybe TD&H did the dirt side of it.
Why'd you say it like that?
I'm not saying that in a bad way. All right. I'm not saying that in a bad way. All right. Some people like the dirt. Okay. There's nothing wrong with that. All right. Okay. No judgment. Damn. I still think they're just like way too conservative, but anyway. So Sutton's even in here, okay? He pulled together some loading information for the project. Let's hope he's right, all right? We've got ASCE 716, we've got the sign loads, we've got the big-ass sign, it's 40 pounds per square foot, okay, of sign area, right? Lateral loading, well, we have 25 pounds per square foot of wind load projected on the sign itself. We've got an earthquake load located at the center of the sign, center of mass. The lateral system, this is a non-building structure, okay? We're not in chapter 12 of the seismic of ASCE 7, we're actually in chapter 15, which allows you to design signs and billboards, and they have parameters around designing a sign and billboard, so that's what this was designed around, okay? Sign framing, okay, just assume the internal sign framing is designed to span horizontal, okay? So if you have a earthquake load at the center of the sign, imagine that there's all these lateral elements, right, that are horizontal elements that allow that load to just span horizontally to our pipe columns, okay? Framing, I'm giving you some drawings out there. We'll walk through those connections. They're also in the drawings. The layout also in the drawings. Okay, you can ignore the fact that these columns are filled with concrete. Okay, and ignore that this thing's sitting on a big concrete mat foundation, and ignore having to deal with like designing this sign. Okay, I think everything's here that you shouldn't need. Okay, so your firm has been selected to increase the height and size of the stadium scoreboard. I don't know if you remember this scoreboard was a lot different a long time ago. Okay, you're tasked with developing the finite element model of the columns. The project manager for the project has already developed some of the details for the architect's review and is presented to you for confirmation. This happens all the time. Shit will go out the door because someone has done it a lot. Okay, have you guys seen that? Or they set a drawing set to you guys, right? And it says 100% design development, right? Or 20% or 25% construction documents, CDs. Okay. The architect has seen that, right? You're in the verification stage, really, right? And that happens a lot, where shit gets drawn and it gets kind of pushed out the door a little bit. People start seeing it, and then us get to come in and we're gonna grind through all the numbers and make sure shit works. And hopefully, if you have a good project manager, they have done this enough and that they're pretty close to the right answer right out of the gate, right? And you don't have to come to them and say, wow, we gotta like double the size of this column. And then they have to go back to the client and say that too, right? And they become the bad guy though, and you don't, right? So they asked for, their biggest concern for your analysis is the plate connection where the two different size pipes meet, right? So there's a pipe coming down, it lands at this connection at a given height, and it turns into a bigger pipe, okay? We need to model this, okay? This is a picture of that top pipe and what that connection looks like. If we go through, okay, I want you to create a VA model that focuses on the connection of the two pipe columns, okay? That VA model should have a model description with it, right? That just given, just do that, okay? Just as you've done in all of the last 2 homeworks, okay? Also, use hand calculations to verify 2 aspects of your model results. You get to choose this time, okay? I'm not gonna ask you to do certain things, okay? I don't wanna get ridiculed on how dumb they are, okay? Okay? I want you to come up with your ideas of what you would pick out of your model to verify your model, right? But they need to be valuable, right? Don't just pick the easiest thing out there and run with that, right? Just, you get 2 things to choose, do that well, okay? I want you to quantify convergence of your plate results, right? You're gonna have some plates in this, and we're gonna talk about it today and on Monday a little bit, about, some methods you can use at these interesting interfaces between, say, a member element and a plate element, okay? Provide the maximum stresses you would use in evaluating the adequacy of the following components, right? Think of your mechanics and materials days, right? You're gonna have a model, it's gonna give you all sorts of results, right? And I want to know what is the maximum stress you would use to evaluate the adequacy, right? Because you're gonna actually have sizes based on the drawing. So what's the top column base plate? What's a critical stress or stresses that you would be looking at in designing that plate? The top column stiffeners, okay? Those are these vertical elements, right? They're a foot tall that run from the outside edge of the plate all the way up. And then the bottom plate, right? The bottom column cap plate. Yes.
Do you want us to, we're doing like our loading for the actual column.
Mhm.
Is it okay to idealize everything as like a point load acting at one point, or do you want it distributed over the height of the sign?
You decide, and obviously in your model description, you can make a description of why you maybe made that choice and why or why not, knowing the intent of this and the focus is that connection, why or why not you could make that simplification, right? And how it may or may not affect the connection, right? 'Cause in the end, you want to be as accurate as possible for the connection itself. Okay?
Is the bottom column cap plate at the base of the whole thing? Is that like the bottom of the bottom?
No, so the bottom column cap plate. So it's we're looking at that large column, and there's a cap plate that sits on the top that this flange
So
plate
there's like
holds.
2 plates, one on the top.
Yep.
one on the
Yep, and that's where, I'll show you here, Greg, whoops. These are the drawings, there's 2 sheets, okay? I boxed out the details that are pertinent in red, right? You guys are so well versed in reviewing these, right? These are structural drawings, okay? One that's very important is a scoreboard elevation view, right? This is just looking at the scoreboard. There used to be, you guys have probably been around, right? This is Revit, baby. There used to be a roof structure under here. There used to be a locker room and stuff, right? They demoed all of this. Now the Valcat Athletic Complex sits right behind this, okay? This is that connection, right? We have upper column, lower column. They give you the size of the scoreboard, okay? They give you where that scoreboard's sitting, okay? They give you some call outs to details, right? These are little detailed call outs that say, okay, go to 11 on S, I think 2.4 or something like that. So I say 11, here's this connection, right? We've got a bottom cap plate. This is the bottom column cap plate, right? So this is the top plate there, right? It is 2 inches thick times the lower pipe diameter, okay? The column call out is on the elevation view, so you know what size this is. You can figure out what size this is based on the elevation view. They give you how thick each one of these stiffeners are. They tell you that there's 12 of them evenly spaced around the perimeter. They tell you how high that is, right? They tell you what type of welds, okay? So you can make an evaluation of what type of fixity you might want to put on these stiffeners, okay? And then obviously this whole connection is going to have loads on it, okay? Scared?
You look so amused.
I fucking love this. I would love to do this. I'm excited to see yours and then I'll do it myself, but it's fucking cool, okay? Something to think about, okay, maybe we'll just jump into it because we're running out of time today already, is what are some of the...
Do you want us to account for,
What?
sorry, the field weld you have on there?
No, don't worry about that.
Just the bolts.
What? Oh, yeah, so
Bolted
the
and
welding
there's a
is
fuel
final,
welder
right?
on the rest of
Yes,
it.
only worry about the final configuration. What is Aaron talking about? Aaron's talking about the fact that, right, this little flag right here, this is a weld call out, this is a fillet weld, okay? This flag means that it's done in the field, okay? Obviously, they had to like, in the picture it shows, they picked up the top column with a crane, they brought it over and they set it down. If you saw in that picture also, there was these, they had 4 of these bolts that they welded to the top plate so that they could, right, aid in erection, right? Just so that they can take that top one, set it on the top, bolt it down, and they can let go of the crane, and then everything's set up, and then somebody goes up in the man basket, and they weld this off. So this is the final configuration, the final load path of this is the weld. You guys can ignore the bolts, okay? Ignore the bolts, just worry about the fact that at the perimeter of this top cap, right, it's welded down to the lower cap.
Does that mean all the way around?
Yeah.
Yes,
So
yep, that's what that
circle
circle
means,
means,
yeah.
it's all the way around, yep.
Did they end up doing 12-inch tall stiffeners?
Yep, that's what's up there. Okay. So that's what this looks like. Something to think about, and we're gonna talk about it on Monday. All right, but is the fact that we need to consider the interface of members to plates. Okay. One big example we'll talk about is foundations. Right? We have a concrete pier that maybe lands on an isolated spread footing. Well, in the model, we're gonna model this spread footing with plates, right? In the model, what are we gonna model this out of? Member element, right? So in the model, it looks something like this, right? What the hell's going on? Is there something that might become an issue right here?
Huge, highly
Huge.
concentrated point.
Right, and how accurate is that depicting this? Not very accurate, right? It's like assuming this column is coming down and it's just held on by that tiny little piece, right? Onto this footing. And so how do we get away from that? Well, we end up using rigid links, okay? Any ideas of how we might use rigid links to make that happen?
You could offset some nodes from the center and then use rigid links from that to
Yeah.
into those nodes.
Yeah, so we can,
Use a mesh of rigid links.
well, so as we know in FEA, where are elements connected? At nodes, right? So if we had a spread footing, okay, and we had a column coming down and it has a single node there, but we know that actual column, maybe it's 18 inches square, right? And it's coming down here. And instead of, having an interface that's just at one individual specific node, we want to make an interface of these plate elements along this perimeter, right? We want to make it feel like there's an 18 by 18 square column that's bearing and pulling up and down on this footing, okay? So what can we do? Yeah, spider it. We can start adding nodes around the perimeter. And maybe we'll put some rigid links or some infinitely stiff elements, so that when this rotates, right, based on the stiffness of this pier, it's going to rotate this whole thing, right? Because if these are rigid links, they're infinitely stiff, right? When this pier rotates and this node rotates because of it, all of these nodes have to rotate together, right? And so then if you connect this plate to all of these nodes, right, whatever that might look like, then you get this nice like interface where you're interacting the two together. Yes.
It's unrelated, I'll ask you later.
Okay.
Well, actually,
No.
if you mesh this, is there a way, like you have that, but that looks like you defined that, like you noted it and then you meshed it. If you just have 4 nodes and then you do like an auto mesh, is there any way to impose boundary conditions on the auto mesh nodes so that?
Yeah, you can, so like on that's an area. I just drew an area.
Yeah, and then mesh.
And then auto meshed it, and it takes all the nodes in the plane and it connects it. So it auto connected to this single node that the member's framing down into. Okay. And so in VA, if you get to play with areas, they have area sides, and you can click a side, and then you can say fix it. So what it does is, it doesn't physically fix this side of the plate, right? It fixes the nodes that are on that side that it generated automatically. So it's its way of imposing the boundary conditions that you would have to individually impose on each of the nodes along a side. But because of the fact that you're not actually making these plates, it needs to know what type of boundary conditions to impose along that edge. So you have to get it done.
Why are you using an area and not a plate?
Because it's way easier to
Then
mesh
use
it.
auto mesh.
Yeah.
And then you change it into plates?
Yep, and then you can generate plates with an area, so then it actually doesn't make the plates. Like, you can't go and click on each one of these individual plates. You can also take this area, and once it generates to plates, you can, what is it called, like, you can essentially make plates. So you can export the plate configuration to actual plates, and then you can click on each individual plate and mess with it just like you normally would. In the educational version, you don't have the option to use areas. So you got to mesh that by hand, right, individually. Just start drawing plates. Or you can take plates and start copying them over, right? Especially if it's circular, there's a copy paste function in VA that you can do cylindrical coordinates. So you can pick a center. If this was a circular column, you can say, all right, I created a node here, right? And maybe I created a node here and I made a plate just like that, right? And I can take this plate and I can copy it around this node, assuming this is the axis of rotation.
So we want to converge our plates in the educational version. We have triangles like, so we have to redraw nodes or like.
You would have
delete
to, you would have to
everything and then-
change the number of plates, right? You'd have to refine your mesh, because that's the whole idea behind convergence. That's why I said quantify convergence. So essentially, I mean, you don't necessarily have to, you have to feel comfortable with the values that you have.
Yeah.
And so, start at a refinement and work your way through and just quantify it, meaning like document the fact that, okay, the stress was 100 PSI, then it changed to 200 PSI, then it changed to 225, then it changed to 226, something like that.
But we can't just, I guess I'll
Look at it. Yes?
You have a 9/16 weld around the circumference of the upper pipe.
Yeah.
Can we assume that the the edges of our pipe aren't like added by that weld? Like that weld, you know what I mean? Like when we're setting our diameter of that pipe, do you want us to add a little bit?
No, you can assume that's just the plate diameter.
Okay.
So is that model right there just the 18-inch column on the notes? Like, is that the?
Yes.
Okay. that's-
Yep, so this would be just saying, I have a 18 by 18 column, and it's running down onto a 5 by 5 square
Okay,
footing.
so that square is the footing, not.
Yep, this is the area of plates, that is the footing, that's this guy.
Or you were saying we could model the 18-inch column to look probably just like that, but that would just be the 18-inch column?
It's weird that you don't have, because don't you want those are the rigid links going up?
No, he doesn't
No,
have
so I have
rigid
none,
links.
is
Oh,
that
okay.
rigid links become useful
So
because
you
you have this problem where you need to consider the interface of the members and the plates.
Oh,
Because you don't really want this.
okay.
You don't really
You
want
have
this.
those-
Unless you're not really worried about the plate stresses, right? 'Cause you're gonna get some really high stress concentrations because out here you're gonna have like no stress, and then here you're gonna have all the stress. And it's gotta linearly change between one or the other. So it's gonna start at like 0 and it's just gonna ramp up like crazy to get there. So you wanna be able to refine this and make it more gradual, and you can do that by this. Something to think about when you're doing this though, right? When you interconnect all of these things with rigid links, now you essentially have this infinitely stiff 18 by 18 block in your footing also, right? Something to think about. But that's where rigid links become incredibly powerful to help you figure things out. And you can impose boundary conditions on those rigid links, right? Maybe you want to allow this plate to rotate, right? But you're only going to affect the translation, right? And so you can then say, all right, I'm gonna let this rigid link rotate on that node, but it's not gonna let go of it, right? So it's going to be pushing up and down and twisting around, but this plate can then rotate, right? Because it's not gonna be fixed by all of these rigid links. You gotta think about boundary conditions.
Are the rigid link releases similar to like element releases?
Yeah, it's essentially an element, a beam element that's infinitely stiff.
You just drop down in the member. It says standard parametric or database shape.
Yes.
Rigid
Yeah.
link, and it still has the same releases.
Okay.
Boxes and.
Sorry, yeah, that's, I didn't get your question, Madison said. Okay? Fuck yeah, alright? And we'll finish, I was so hoping to get to this thing, okay? One of my favorite books.
I bought one and I won't use it, it's fine.
You will too use it.
In class? No.
Who cares about that? It's good to have it.
Yeah, it is good to have it. We're gonna go through it in class on Monday, okay? We are going to have a tour of the field house, all right? I'm waiting for confirmation, but it should be 3 o'clock on Wednesday of finals week, so the 11th, okay? Were you shaking your head for Dawson? Did that work or not work? Why?
Gotta do the Lord's work.
Bummer.
Dynamics teaching.
Dynamics teaching?
Good lord.
Seriously? Are you, you're a TA? How many people come in for that? Probably a lot.
They'll probably be just stressed to the max.
Yeah.
Finals Thursday, so.
Fuck. You don't want to take a tour of the field house?
Can we come watch it?
He does
Yeah,
want to.
Oh, I remember those.
If no one's there, I'll just.
Dawson, that's,
Okay.
that's 2 weeks, right? The finals in 2 weeks?
Yeah.
Yeah, it's finals week.
That's
I
when
mean,
it's finals.
Yeah, finals week,
Not
Wednesday
next
of
week,
finals week,
Oh.
yes. Not this coming week, but the following week. And then we'll try and meet out at the house after
Don't we
this.
have like Lundgren coming next?
John Lovegren is coming on
Lovegren.
Wednesday,
I was thinking
Next
next
week.
week.
okay? Which he's gonna go over Ram.